Welcome to the presentation on organic chemistry. Um, the first thing we want to look at is the idea of organic chemistry. The reason why we have organic chemistry as a separate branch is because of the unique way that carbon has the ability to bond. The ability of carbon to form four bonds is pretty unique. Silicone can do it to some extent, but the ability of carbon to form not only four bonds but with multiple bonds with different atoms actually produces a large number of molecules, and hence that's the reason why carbon is considered to be an organic compound, is because it has the greatest ability to form multiple bonds. And that's the belief as far as why we are carbon based life forms, is because of carbon's unique ability um, to form multiple bonds. So organic chemistry is the basis behind the carbons, chemistry of carbons. So now when we look at the structure of carbons, like we said, carbon can form four covalent bonds, or three or two, depending on what it's bonded to. So what you see right here is an example of when it's bonded to four things. Remember, we call that sp3 hybridization, based on the fact that you have an overlap of the s with the p's, and then p and p. So we have a hybrid orbital. Instead of having an s and then three p orbitals, we have one hybrid orbital that kind of puts them all together. Whenever you have an sp2 hybridization, okay, that's when you have trigonal planar, and that indicates that you have one double bond. And if you have a triple bond, that indicates that you have sp hybridization, which is linear. Okay, so there are four basic types of hydrocarbons. The first one is an alkane, and an alkane is one in which there's only single bonds, and this is kind of a review, and it follows the formula CnH2n plus 2. Okay, whenever you have an alkene, that means that there's the presence of at least one double bond, and it's going to follow CnH2n. And then when you have an alkyne is going to be CnH2n minus 2. Okay, so that's the way that you can predict whether it's going to be an alkane, an alkene, or an alkyne. Now, if you have something that has a ring structure, specifically when it's called an aromatic hydrocarbon, that means it's going to have a benzene ring. Now, a benzene ring is going to look like this. Okay, so it's got the circle to indicate that it's a hybrid structure, but really, if you were to draw it out with the bonds, double bond, double bond, double bond. So if you were to look at this, the aromatic ring, the benzene part of it is C6H6, which doesn't follow any of these rules right here that we have. So those are the four basic classifications of hydrocarbons. Now, we look at them in a little bit more detail. The reason why we have an alkane is only single bonds, and it's said to be saturated with hydrogens. In other words, it has fully it's used up all its ability to bond with other substances with hydrogen. So when we talk about something like a saturated fat versus an unsaturated fat, it's talking about whether this carbon has a double bond in it. This right here would indicate the presence of, if it was attached to a lipid, which we're not going to get into, but if it was attached to something else, this would be considered to be unsaturated. It's an unsaturated fat versus something like this, which is considered to be a saturated fat. Okay, some of them are good for you, and some of them are not, depending on what your dietary needs are. But a saturated one tends to be a little bit better than an unsaturated. Okay, so the formulas are, you see this right here, the Lewis structures. You can draw the structural formula like this, but sometimes that's not very useful, and it's also kind of a pain. So instead we kind of group things by carbons. So you can actually say CH3, CH2, CH2, and then CH3 at the end. Okay, that's the most common way of being able to write these alkanes and alkenes, is by actually writing them based on a carbon basis. So that way you can see the connectivity a little bit better than you could otherwise. Okay, so whenever we condense these formulas, we would call these things something like C4. It looks like it's C4H10. So that would be that right there. And then you can name it as, in this case, it'd be butane. Now, one of the interesting things about when you look at the properties of alkanes is as you get larger, the boiling point increases. Now, remember, the boiling point is associated with intermolecular forces. So, whenever we looked at the boiling point, we would say, oh, wow, the boiling point's a lot higher, so the intermolecular forces are greater, it must be more polar. All of these substances right here, all these alkanes, are considered to be nonpolar. which means there's going to be no interaction as far as a dipole-dipole interaction or anything along those. So what takes over is what are called van der Waals forces. Okay, the van der Waals force, the London dispersion force, means you have the temporary dipole that's set up. So if you have a small molecule, you can make a temporary dipole where it's a partial positive and a partial negative. The problem is, because it's such a small molecule, it doesn't end up taking over for the entire particle. It's not likely to happen very much because of the small nature in which the positive and the negative charge are there. The larger a molecule gets, the more polarizable a molecule is in terms of these instantaneous London dispersion forces. So because of that, as you increase the length of the chain, you actually increase the boiling point as well. In addition to that, when we're talking about the boiling point, we're talking about giving it enough kinetic energy so that this substance is no longer confined to gravity. Whenever you're trying to give it enough kinetic energy for it to escape, remember kinetic energy is dependent on the mass and the velocity squared. Well, the fact that this thing is more massive means it's going to have more kinetic energy in order to achieve this escape velocity. So the structure of alkanes, the carbons are always going to be sp3 hybrids. So the reason why is there are no double bonds. Because there's no double bonds, you're going to have always sp3 hybridization. There's always going to be 4 bonds. Okay, generally at least one of those is to another carbon. It's usually going to be 2 carbons if they're those middle ones, which means you're going to have 109.5 bond angles. Now, when you look at these structures of the alkanes, one of the interesting things and one of the ways we can identify alkanes is the fact that because there are only single bonds, these bonds right here, these things are free to rotate relative to one another. So we can actually use something called infrared spectroscopy, and we can actually give it just enough energy for it to rotate, and we can measure those rotations. So if you're generally looking at the microwave spectrum at this point, but because of this right here, you can actually use it to detect the structure of alkanes. Now, alkanes are generally unreactive because they're usually pretty stable. This is a very stable bond. It's a nonpolar bond, so it doesn't have a great deal of polarity, but they are stable solvents. In fact, they make really good solvents because they're stable, because they're non-reactive, and because they will dissolve other nonpolar substances. Okay, so whenever we have something that's an isomer is something that has the same molecular formula but has different connectivity. The atoms are bonded slightly differently. So this right here gives you an example of butane. Okay, you have butane right here, and then you have something called isobutane right here. And it's all about the connectivity of the atoms. Here, all the carbons are in a straight line across, and the hydrogens are attached on the outside. Well, here you have 3 carbons in a row, but then you have another carbon that's attached to that middle carbon. So you have a carbon that's attached to 3 carbons on either side instead of the straight long chain like we had in the previous one. So as you increase the number of carbons that are in a compound, you increase the potential for isomers. So here you see pentane, and then you have isopentane, and then you have neopentane, based on the connectivity of the atom. So as you continue to increase up, whenever you're doing this, it says they have the same molecular formulas. So in terms of mass, they're the same. So now you have to look at the connectivity of these things to determine, okay, well, which one of these is more polarizable? Because that polarization is going to affect the boiling point and the melting point. Now, whenever you're looking at the nomenclature, nomenclature is dependent on 3 parts. The first one is how many carbons there are. That is the base of all naming structures. So, for example, if there's one carbon, it's going to be meth. Okay. Now, if there's substituents, okay, how many are there and those sorts of things, that's what's going to determine this. The last part tells us what kind of or what family it belongs to. We're going to get into the different families, but whenever you have something end with an ane, that means it's an alkane. If it ends with an ene, that means it's an alkene. If it ends with an ine, that means it's an alkyne. If it ends with an al, it's an alcohol. If it ends with an one, that means it's a ketone. So there's lots of different families to go into. And the last thing that you have is this idea of the prefix. And the prefix just kind of tells you where the carbons are attached or what the longest chain is. And we'll get to that in a couple of examples. So the first thing you do is whenever you name an organic compound, you have to find the longest continuous chain of molecules. So what we do right here is this right here. We start here at this carbon, and we go 1, 2, 3, 4, 5, 6. Because that, the base of this thing is hex. Okay, I look and I say, okay, are there any double bonds? All my carbons are saturated, it looks like. They all have single bonds. So I know it's going to be ane. So I know it's going to be hexane. But I have to account for the fact that there's this right here is not attached in the hexane. There's no name associated with it. So because of that, I need to say that it's a methyl that is missing from this thing, and I need to say where it is. And the way you say where it is you say, okay, it's attached to the second carbon. So since it's attached to the second carbon, it's called 2-methylhexane. Now, you may be asking yourself, well, what if I started counting here and went 1, 2, 3, 4, 5, 6? And that would be a perfectly valid way to count, except for the fact that we always name these substances based on the lowest possible number. So once you've kind of drawn out your continuous chain right here, once you've done that, you say, okay, well, if I start counting here, I'll have a 2, but if I start counting here, I'm going to have a 5. And that makes you determine which way you're going to count. So it ends up being 2-methylhexane. So if you look at this one right here, I'm going to go ahead and kind of scroll down from the name. You say, okay, here's 1, 2, 3, 4, 5, 6, 7. That's the longest continuous chain of these particular carbons. You could also start here, 1, 2, 3, 4, 5, 6, 7. It doesn't actually matter in this particular case. So what I have is I have 7. So that's going to be hep, because there's 7 of them. There are no double bonds anywhere in this particular thing, so I'd say heptane. But now I have to specify all of these particular groups. This right here is a methane. This right here is an ethane. This right here is a methane. And this right here is a methane. So I know as far as methane is concerned, I'm going to have a 2, 4, and 5 methyl. Now you don't have to write 2-methyl, 4-methyl, 5-methyl. You can just say 2,4,5-methyl. And then you also need to account for the fact that you have this ethane. Now whenever you do this, it says if there's more than one substituent molecule, you list them alphabetically. Well, ethane comes before methyl. So because of that, we would call this 3-ethyl. Oops. And then you would put 2,4,5-methyl heptane. So we end up with 3-ethyl 2,4,5-methyl heptane. So you can see how this can be kind of a confusing way of naming things. But that's what we check, 3-ethyl 2,4,5-methyl heptane. So now we've talked about the cycloalkanes, and cycloalkanes are basically whenever you have a ring structure. So anytime the hydrocarbon connects back to where it started, that's what we call a cycloalkane. Whenever you have a cycloalkane, you can see that you can make it out of anything. But the problem is, these right thing here are so constrained that it doesn't actually work. And here's the reason why. Remember, whenever you have carbon that's attached to 4 things, the bond angle that it wants to be at is 109.5 degrees. Now, whenever you're trying to make a triangle, you should know that in a triangle, that's going to be 60 degrees. So in order to take and make this work as far as a cyclopropane, which would be a 3-carbon ring structure, you'd have to take and you'd have to bend these atoms to be a whole lot closer to each other than they want to be. So because of that, you tend to not see things that are 3 carbons. Instead, you tend to see things that are 5 to 6 carbons. Those are the most stable ones based on conformation. Conformation just means the attachment of the atoms so the bond angles match the angle of the ring structure that you're trying to make. Next we have alkenes. Alkenes are very similar to alkynes. They have very similar properties. The biggest difference is that they have a double bond. So because they have a double bond, they are considered to be unsaturated because they have fewer than the maximum number of hydrogens they are allowed. Okay, unlike alkenes, alkenes are not free to rotate. Now remember, when you have a alkene, the reason why these alkanes could rotate relative to one another is, remember, they have direct overlap of their electron clouds. This direct overlap of the electron clouds, you can rotate them in 3 dimensions and it doesn't matter because they have direct overlap. Now, whenever you include a pi bond in here, remember pi bonds are overlaps of these kind of sideways orbitals. As a result of that, if you were to rotate one of these things in 3 dimensions, these things would no longer overlap. Because they would no longer overlap, the bond would break. So because of that, whenever you try and rotate these particular structures, it cannot rotate freely. So as soon as you have a double bond, these things are locked in place. So whenever we draw all of these things right here, as far as hydrogen, hydrogen, and hydrogen, because it's a single bond, they're free to rotate relative to one another. So if I put a chlorine here and a chlorine here, these atoms can rotate relatively easily with one another. It doesn't make any difference. But as soon as you put that double bond there, they're locked in place. So if you have a chlorine there and a chlorine there, it's going to have a certain name, as opposed to if you have a chlorine here and a chlorine there. It's going to make a big difference. Okay, so whenever you have this, you have what are called geometric isomers, and that's what we were referring to in the last slide. So the fact that you have something on one side or something on the opposite side. Okay, so these are geometric isomers where everything is the same from here to here, and the only difference is this group is here and this group's here. They're diagonal. That's called trans. Or this right here and this right here, where they're on the same side, it's called cis. So whenever you have two functional groups that are on the same side, it's called cis. Whenever they're on opposite side, it's called trans. So whenever we look at the properties of alkenes, because they have different structure, if you look, whenever you have the double bond, where the double bond is and how many things are on other side will affect the properties of them, but not nearly as much. If you look, the boiling point is -7, -6, +4, and +1. Those are all relatively close to one another based on the geometric structure and the double bond. Okay, whenever you look at the nomenclature, it works the exact same way as the alkane. You find the longest carbon chain that you can. Once you find that longest carbon chain, you count the number of carbons, and in this case there's 5 carbons. So because there's 5 carbons, it would be pent. The only difference is that now that you have this right here, you have to call it an ene. Whenever you call it an ene, like pentene, you need to specify exactly where the double bond is. Now remember, we want to name our functional groups based on the fact that they are the lowest possible number. So if you were to number 1, 2, 3, 4, 5, okay, this would be 5-pentene or 4-pentene. You don't want to do that. You want it to have the lowest possible number. So I would say 1, 2, 3, 4, 5, and as a result I can call it 1-pentene. When you look right here, this right here is pentene because I have 1, 2, 3, 4, 5. So that's pentene. Now the fact that I can have this double bond right here, the double bond is on the second carbon because I can go 1, 2, 3, 4, 5. So I know it's going to be 2-pentene. Now the last thing that I need to do is, because I have some geometry here associated with this particular bond, I need to say, okay, well, the two functional groups, this part right here and this part right here, are on the same side of the double bond. So because of that, I call it cis-pentene, so it would be cis-2-pentene, and right here they're on opposite sides, so it would be trans-2-pentene. Okay, whenever you have a reaction, alkenes, you can do what's called an addition reaction fairly easily. Okay, if you have bromine right here, both of these things. Okay, when you have bromine, bromine wants electrons. So because of that, these electrons right here can be donated to this bromine. Whenever they're donated to this bromine, it can kick off its electrons right there. And then you have a bromine that's negative, and you have a bromine that's attached now. Well, the problem is now, remember, these carbons shared these electrons, and now those electrons are right here attached to this carbon, so that makes this thing a positive charge. But when it's a positive charge, it will attract that negative bromine, and now you have this right here. So it's pretty easy to add something, especially something negative, across a double bond. You have alkynes. Alkynes are the exact same thing as alkanes and alkenes, except for the fact that they have a triple bond. Because they have a triple bond, they have to be sp hybridized and they're still unsaturated. Okay, now whenever you do the nomenclature of the alkynes, it is the exact same thing as we've been doing. Same rules for methyl 2-pentyne, except for the fact that instead of an ene, it's an ine. Okay, whenever you have reactions with the alkynes, it's pretty easy to kind of attach things to it. So you see the example of chlorine, something that wants electrons pretty easily. So you can go there, and then it can go here, and you can get 2,2,3,3 tetrachlorobutane. Whenever you have an aromatic hydrocarbon, that is something that contains a benzene ring. Whenever you have a benzene ring, a lot of times we draw it with a circle to indicate that it's a hybrid structure, or it's a hybrid of several resonance structures that you have there. It is a planar molecule. All of these carbons exist in the same plane. Whenever you are naming these things, there are certain common names that are associated with them. These aren't technically the names that you're supposed to call these things, but they are common. So you can see something like benzene and naphthalene, and anthracene. Toluene you see kind of a lot. And then toluene is actually methylbenzene. Now the reason why toluene comes up a lot is because it's used quite a bit in organic chemistry as a solvent. Whenever you look at the reactions of aromatic compounds, so alkenes and alkynes really want to get rid of these electrons, but whenever you look at it in terms of alkenes and alkynes, there's no, the delocalized nature of it stabilizes this. So benzene structures are particularly stable because of their delocalized structure. Because they're stable, they're not very reactive. In fact, benzene is one of the best solvents you can have for organic compounds. So whenever you attach things to benzene rings, there are certain names for it. Ortho means that they're on adjacent carbons. So if you have two things right next to each other, it doesn't matter where they are as long as they're next to each other. That's called ortho. Whenever you have one carbon in between them, it's called meta. And then finally, when you have them on opposite sides of a ring structure, it's called para. Now what you see right here is this is dinitrobenzene. Okay. If you were to kind of flip back, we saw this right here was called toluene. Okay, so if you were to do something called trinitro toluene, that is actually TNT. So we go back and we say, okay, the last thing we need to talk about is the different functional groups, which can change the name and the identity of our compounds. We're going to give kind of a brief overview of what these are, but they're all listed right here: alkenes, alkynes, alcohols, ethers, haloalkanes. But let's go into them in a little bit more detail. So anytime you see a hydroxyl group that is not associated with a base but instead with a hydrocarbon, it is called an alcohol. So what you see right here is this is propane, but because there's an OH instead of an H, we change it from propane to propanol. Now we do need to specify the fact that the anol is associated with the second carbon as opposed to the first one, so it's called 2-propanol. Now, the kind of alcohol that humans consume for the most part is CHHH, COH, like this. Now in this particular one, I do not need to specify the fact that this hydroxyl group is on the first carbon because it's implied because there's only two. So it couldn't go anywhere else other than carbon number 1. So this is called ethane because you've got two carbons. So eth, and then instead of ane, I put anol. So it's ethanol. But then you see things like propanitol. And then cholesterol is even considered to be an alcohol because of this little group right here. So whenever you have alcohols, these are just examples of other alcohols that you see right here. So propanol is used for rubbing alcohol. Okay, is isopropanol. Okay, you see T-butyl alcohol, which is methyl 2-propanol. So there's all kinds of different names for these things, and you may have seen some of these things before, like glycerine and glycerol. Okay, phenol is a big one if you're going into genetics, because you can actually use phenol to denature DNA pretty easily. Now, whenever you have something that's called an ether, an ether is something that you have an oxygen that exists between two carbons. Now, it doesn't actually have to be double bonds right here. It's just you have two functional groups, something like this, and an oxygen in between them. Now, ethers tend to be quite unreactive, so they tend to be good solvents for the most part. There are also carbonyl groups. As far as carbonyl groups, there's a bunch of them. Carbonyl groups contain a C-double-O bond. So we have this particular bond right here. Now, whenever you have a C-double-O bond and a nitrogen, it's called an amide. Whenever you see a C-double-O and then an H, it's called an aldehyde, like formaldehyde. Whenever you see C double bonded OOH, it's a carboxylic acid, like you see in some DNA structures. Whenever you have C double bonded O and then attached to another carbon, okay, that's what these R means. It means other carbons. That's an ester. And finally, if you have a C double bonded O, it ends up being a ketone. So when we look into these in more detail, at least one hydrogen is attached to it. So if we were to name this particular structure, you have 1, 2, 3 carbons. Because of that, I can say methyl ethyl prop. So this is going to be prop. And then I have to name it with an ide. Okay, so it's an aldehyde. Okay, whenever you do this, you'd say, okay, there's 1, 2, 3, 4, 5. So we'd say, okay, this is pent. And then we would name it as an one. And we have to specify which one this is actually on. So we'd say carbon 1, 2, 3. So it's 3-pentone. When we look at the carboxylic acid, we'd say, okay, this right here is 1, 2. So I can say that 2, actually I wouldn't do that, I would say 1. And because of this 1, because you can count it back this way for it to be smaller, you would say there's 2 carbons. So you would say ethoxylic acid. Now we tend to not call this thing ethoxylic acid. We tend to call it acetone instead, or acetate. Because you see a bunch of examples. You see methanoic acid, citric acid, acetylsalicylic acid, which is aspirin. There's a whole bunch of these as examples of them. When you have an ester, esters are an example where you see the C double bonded O and then the O after that. There's a little bit different naming reaction as far as that's concerned. You take the smaller one, regardless of what side it's on, you take the smaller one and put it out front. And then you actually end up with the second smaller, or the larger one becomes this, and then you add an 8 to the end of it. And esters are really found in perfumes. So whenever you have amides, it's very common for you to have the C double bonded O and then the N, and then you have some sort of other reactant group right here. When you have amines, generally these things are organic bases, like you see ethylalamine or trimethylamine or phenylalamine, which you actually see quite a bit. They tend to be organic bases associated with the fact that they have these lone pair of electrons on the nitrogen, so they tend to be able to donate those.